All right, CNT120, Chapter 5, we're moving into the section on fiber optic. Now, I put this in here first. It kind of got buried in the chapter, but most of the fiber connections we're going to deal with are a two-fiber connection, meaning one is for send, one is for receive. One is for sending the signal, one is for receiving the signal. Just keep that in the back of your brain. That's why I showed you two examples here. A lot of the fiber connections we'll deal with in networking are two-strand, one send, one receive. All right, if I cut apart the fiber that we're going to typically deal with, here's what I find of its construction. There is an outside jacket. This is the protection for the whole cable. And again, this is actually, they have plenum rated and riser rated jackets on fiber as well. We'll see OFN-R for riser, optical fiber non-conductive riser, and OFN-P for plenum. So again, looking at that last letter R and P will let us know riser or plenum. As I cut away the jacket, I'm going to find these strength fibers. These strength fibers are typically Kevlar, and they're there for protection on when I am installing the cabling, protection that I don't actually pull the cable too hard and break any of the fibers that are inside. Next, I'll find this actually is the glass strand part of the fiber. And that glass strand, I would literally need to put under a microscope to see the difference between the core and the cladding. The cladding is the outer glass around the outside that's designed to keep the signal in the core. And then the core of the fiber is the super clear glass that actually carries your light signal, carries the actual pulse of light. And that core, the whole glass fiber is about the size of a human hair, and the core would be like the center of that hair, kind of like the little bullseye in the middle of that hair, letting you know the size of this stuff. It is very small. Our fiber optic pros and cons, they put this early in the chapter because we need to think about when would I be using fiber optic. It is more expensive to deal with, so there has to be a reason. It is immune to electromagnetic interference. It's immune to any kind of electrical noise. The light moving through the glass fiber is totally not affected by any electromagnetic interference. And as I like to say to people, take a flashlight and put a magnet at the end of that light, and the light does not get affected by a magnet there. It is not affected by that magnetic field whatsoever. So my fiber optic is not affected by any electromagnetic interference, which is typically the source of most of our noise or problems in data signaling. It's very resistant to eavesdropping or tapping, if you will. It supports very high data rates and allows much greater distances than your twisted pair cabling. Sometimes kilometers to tens of thousands of kilometers in distance. The downside is it's expensive. It's more expensive to buy. It's more expensive to deal with. It's more expensive to terminate. And I can't use pretty much any of the tools I have for twisted pair to deal with fiber, including the meters. I pretty much need a whole new, toolbox, if you will, including meters to work with a fiber optic. There we go. Okay, there is two different types of fiber. There's single mode and there is multi-mode fiber. Okay, let's talk single mode real quickly. Single mode fiber, my core of my fiber is very small. We're talking 8 microns to 10 microns in diameter. Now, just to give you a heads up, when I see these numbers up here, 8/125 or 10/125, what they're showing you is the core to cladding diameter. So the core of this fiber is 8 microns. The cladding of this fiber is 125 microns. Now the 125, that would be the cladding here. 125, think about that as the size of a human hair. That's about 125 microns is the size of a human hair. So the core is very tiny, and the cladding out here is 125 microns. My single mode fiber is going to transfer data through with a single ray of light, single mode of light, single ray of light, single mode of light. And it's typically going to be using a laser to send that signal. So think of a laser pointer that you have. Even that, $1.99 laser pointer that you have as a key ring, when I shine it across the room, it still stays a pretty focused beam on the other side of the room. That's the whole point of a laser light source for single mode fiber. I have to hit that super tiny core, and that laser light is focused that I can shoot that laser into the core of the fiber, and it's going to stay focused. And I'm literally sending a pulse by followed by nothing. Pulse of light for 1, no pulse for 0. Pulse of light for 1, no pulse for 0. And that single ray, that single beam, that single mode of light is representing my data signal. I can do great distances with single mode. So this is typically for WAN use, connecting buildings, connecting cities, if you will. Okay, connecting buildings, connecting cities is what I would typically be using single mode fiber for. Here shows you a quick difference. If this were the cladding of my fiber, here would be the core of single mode. If this were the cladding of my multi-mode fiber, this would be the core of multi-mode. So you can see the core of multi-mode is much larger. The core of single mode is very tiny. Here's an example of single mode. It doesn't look any different from the outside. It has to do with the inside construction. Now, they do use different jacket colors and different connector boots to let you know it's single mode versus multi-mode. Just a little heads up on that. That's why I threw that picture in there as an example. Multi-mode fiber, I now have a larger core, 50 microns or 62.5 micron core diameter with a 125 cladding diameter. The cladding diameter stays the same on all of these, and that helps with some of our devices for terminating fiber and things like our connectors and so forth that we're fitting the fiber into. Here I'm going to transfer my data with multiple rays of light. My light source in this case is typically LED, and here I'm sending up multiple rays of light to represent a 1. Now, a lot of people see these and think of multiple signals. No, this is one signal. This is just one pulse of light. That one pulse of light is made up of multiple rays, multiple modes of light moving through. And then when I shut that off, all those go away and I have a gap in my fiber. Then I hit the light source again and it fills up with a bunch of these multiple rays or multiple modes of light. Because of that, my cable lengths are limited. We're talking hundreds of meters now to maybe a few kilometers. So this is typically used in a LAN between closets in a building, between switches in a building, maybe two adjacent buildings on a college campus kind of thing. So we're talking hundreds of meters, maybe a kilometer kind of thing for multi-mode fiber. And again, here is my cladding of my multi-mode, and this would be the core, nice big core. So you can think of this almost as like a McDonald's straw, big milk shake straw, versus over here a little coffee stir for single mode, just to give you kind of like a visual representation between the two. And again, here's your multi-mode fiber. I don't really know any difference from the outside other than the jacket and or the connector boot colors. Those give me a clue as to what it is. And actually, a quick side note. The actual making of fiber optic, a breakthrough happened back in the 60s at Corning Glass in New York, up in New York State. If you go, there's actually a Corning Museum of Glass up there. There is all kinds of neat stuff in there. One little section of the museum is actually about this breakthrough in discovering how to make super clear glass to carry a data signal. And there was 3 guys up there, Keckmauer and Schultz were their last names, that figured out how to make glass super clear. They actually make it from a gas, and they make the glass super clear from a gas, so that there's no impurities in it, so that I can get a nice clean piece of glass to send my light signal through. Just as a little side note there on a breakthrough, it's kind of neat that it's pretty close to home. If you're up in that area, check it out. My fiber optic connectors, there is ultra polished connector and there's angled polished connectors. And the whole idea here is, think of these as if I'm trying to take 2 garden hoses and put them together. Probably at some point in your life you've taken 2 garden hoses and put your hand around them to like get the water to go from one hose to the next. If I do it pretty well, I can get most of the water from one hose into the next one. If I don't do it too well, it's going to spray out everywhere. Well, fiber optic connectors are the same kind of idea. I need to make sure that the light signal from this fiber gets into the core of this fiber. So if I get them nice and aligned and nice and polished, I get most of my light signal from one fiber to the next one. So over the years, there have been multiple fiber connectors trying to find a better way to do this. Early days, we used the straight tip connector, ST connector. There's like a little twist lock connector here. Okay. Then they moved on to SC subscriber connector. This allowed us to get some, the problem with this guy back here was it was hard to get polarity. This could literally twist twist lock connect on either one of these. It was hard to get polarity to know that the sends and receives are getting connected correctly. This one, I could clip the two fibers next to each other and make sure I had the polarity right to connect this in. They moved on to the MTRJ, Mechanical Transfer Register Jack. This, as you see here, is a nice small compact connector. The problem with this one, though, is I had to get two fibers lined up with two connections in there. So fiber alignment was a bit of a challenge. The common one that you see right now is LC, local connector LC. A lot of your fiber connections, especially between switches right now in closets, is going to be these LC connections here into like a SFP that's going to house those LC connectors. That's the most common one you're going to see right now. They do make media converters that will allow you to connect here's a twisted pair connection into a fiber connection. These were very common when you didn't have fiber connectors in a switch. We would use these media converters. Along came hot swappable modules, GBICs and SFP, small form pluggables, that allowed you to slide it into a switch. Here's a GBIC that would slide into a switch. Here's a switch with a GBIC slot. There's one that would slide in. This would be for copper. And here would be ones for fiber that would slide in, allow you to plug the fiber right into the switch. That was pretty common for a while. More modern form, and this is very common right now, is SFP, small form pluggable. This right here, I would have a switch that almost looks like it has an empty slot in, which is what it is. I slide the small form pluggable one. There's a copper one. There's a fiber one. I slide it right into the switch, and then I can plug my fiber cable right into the switch. That is very common right now to have a fiber connection between two switches. But I do need to buy these. I do need to buy these in addition to my switch. So it does add costs. They do add costs. And there's a close-up of one here. This is very similar to the switches we have in our lab room right now. There's the SFP slot, and I slide my SFP right in and then plug my fiber cable into it. So I can have a fiber connection between my two switches. Here's a rundown of the fiber standards for Ethernet. And again, if you break these down, they're not so bad. Actually, let me come back in the next podcast and I'll go through these with you.